And maybe we'll wait for another minute in case people are still working. Yeah, more.
Can you pause the recording?
All right.
Should pause for recording?
I just started the record. Depend on. Maybe go there. But they're working on.
Okay, thank you all for coming to the Origins seminar. Today, we are very fortunate to have Andrea Salazar presenting. Andrea is a PhD student in the Earth and Planetary Sciences Department of Harvard University, working with Robin Wordsworth and Eli Zipperman. She holds a BA in physics from the University of Chicago, where she worked with Dorian Abbott and also Ted Komacek, the student here. Formerly, Andrea is interested in a broad range of climate questions on both Earth and other planets. Some of her work investigates how cloud feedbacks affected Earth's climate during hothouse periods, like the Eocene, about 50 million years ago. Additionally, she also studies the coevolution of planets' climate and rotation rate, combining orbital and climate dynamics to study the evolution of Venus and other rocky planets. So Andrea is using a hierarchical modeling approach, ranging from simple analytic models to 3D GCMs. And today she will be telling us about exploring self-consistent, habitable Venus scenarios using a novel spin climate evolution model. Andrea?
Hey, Daniel. I think I'm going to stand, if that's okay. So I'm so excited to be here chatting with you all about this work that I've been thinking about. As Daniel said, I'm in the last year of my PhD. Working with Robin Wordsworth and Eli Zipperman. And yeah, today I'll be telling you about my work exploring self-consistent habitable Venus scenarios using a coupled spin climate evolution model. Just really quickly, I wanted to give you an overview of what my research interests are and kind of how this project came to be. So when I was an undergrad at UChicago, I was a physicist and I started working with Dorian Abbott thinking about how climate dynamics shape planets' habitability. So I studied the ocean dynamics on tidally locked planets and how that keeps tidally locked planets habitable. But when I started my PhD, I realized I was using these global climate models, but I didn't really understand the climate system at all. And so then I went back to Earth for a little bit and studied cloud feedbacks, such as a subtropical stratocumulus breakup on Earth at high CO2 concentrations. And in my next project, I put these two ideas together to investigate the maximum warming that you could induce on Earth from a complete stratocumulus cloud breakup. And that would be very relevant to future studies of climate change on Earth. And then after my qualifying exam, I pulled a full 180 and I started thinking about the planet's spin evolution. And the first project I did here was studying how the spin state of a planet depends on its atmospheric state. And that is not obvious, and it seems like those two things should not be connected, but I will talk about it a lot in this talk. And so this Venus work is really smack dab in the middle. It's combining all of my interests from climate dynamics to cloud feedbacks to spin evolution. And so it's been kind of my passion project. And it's the final chapter of my PhD. Venus is still a mysterious planet, even though by exoplanet standards, it's our neighbor. And so it's kind of fascinating that we still understand it so little. These are real headlines from popular science articles that are summarizing recent work on Venus in the past few years. And you can see that these headlines range everywhere from Venus was habitable for 3 billion years to Venus was never habitable to Venus has life in the clouds today. And the reason why Venus is so difficult to characterize in terms of its evolution is that all we really know about Venus is what it looks like today, specifically what its atmosphere looks like today. And it's difficult to search for evidence of past evolution on Venus in the rock record because Venus's surface is very young. The average age of the surface is about 0.5 billion years. And this is because it's thought that about 500 million years ago, there was a resurfacing event on Venus, which flooded most of its surface with fresh volcanic material, which kind of obscures the stuff that's underneath, which might record past atmospheric evolution. And on top of that, we don't know what Venus's initial state was, which means when we're performing studies of Venus's evolution, what we're essentially doing is mapping out different trajectories that could have happened and seeing which ones are consistent with the atmospheric state we see today. So here I listed just a few studies that have done this, but there are many, many more. And because of this inherent degeneracy in pathways that can lead to the same atmospheric state, many theories for Venus's evolution have flourished in the literature. One theory is that Venus was habitable for a very long time, for billions and billions of years. Another theory is that Venus formed with water, but that the surface was never cool enough for that water to condense on the surface. So it had a steamy atmosphere, and that atmosphere was slowly lost in time from hydrogen escape. Or some theories say that Venus just formed dry and never really had that much water, and its CO2 atmosphere was outgassed over time. And these are all very different scenarios, but all of them can reproduce Venus's current atmospheric state. I'm going to focus specifically on the habitable Venus question, because that's the closest to my research interests, but all of these scenarios are very interesting. All of you have seen this figure before, so I won't walk through it too much, but this is the habitable zone. And what's interesting about Venus is that it's just outside the inner edge of the habitable zone. But 3 billion years ago, when the sun was about 30% dimmer, Venus could have been habitable if it had the right climate conditions to support it being underneath the runaway greenhouse. And so, for example, what's one way to keep Venus under the runaway greenhouse? I'm hoping for audience participation. Please also ask me questions throughout at any point. So how do you stop a planet from absorbing too much sunlight?
Reflected?
Yes, what's something that is reflective on Earth?
Clouds.
Cloud. I couldn't have planted it better myself. What if Venus was just really cloudy? Venus is cloudy today, but with sulfuric acid clouds. We're going to talk more about water clouds here. And understanding this divergence in evolution between Venus and Earth has obvious implications for exoplanets, because there's this huge population of planets that fall in this Venus-like zone where they're closer to their host star than Earth, but they could be habitable under the right circumstances. And so we really need to understand what happened to Venus. It's right next door. So it offers a really unique opportunity to study planetary evolution. I'm just going to walk you through the outline of this talk. It's okay if each individual point doesn't make sense yet, but we will talk about each one. I just want to kind of show you the map that we're going to make. First, I'm going to convince you that in order for Venus to be habitable in the past, it needs strong cloud cover. And the way to do that is to have it is for Venus to have a slow rotation, like the rotation state it has today. And then I'll show you that Venus's current spin state appears to be in equilibrium between two tidal torques, the gravitational tide and the atmospheric thermal tide. And then I'll show you my work which studied how the atmospheric thermal tide depends on the atmospheric state. So that if Venus had a habitable atmosphere in the past, this would lead to a different spin state than we see today. And this might preclude the strong cloud formation that we need to keep it habitable. And all of this will lead us to the subject of this work, which is a self-consistent rotation climate evolution model for Venus. Okay. So slow rotating early Venus would form strong substellar cloud cover. And I'm going to walk you through why that is true. Okay, here I'm showing you a map of surface temperature for a rapidly rotating planet like Earth, where this black dot is the substellar point. So this is the location on the planet where the sun is shining the most. And this substellar point will move over the course of a day. So as the planet is spinning, because the length of the day is pretty short due to the rapid rotation, you don't form very strong temperature gradients between the day side and the night side. And because of this, the day side's not very warm, so you don't form a lot of convection, which then forms the clouds. Versus on a slow rotating planet like Venus, the length of day is so long that you have these huge temperature gradients between the day side and the night side. And the day side is so warm that you induce convection, and this convection will form very strong cloud cover. And modern Venus today does have a very slow rotation period. It rotates once every 243 days, which is interesting because this is actually subsynchronous. Its orbital period is 225 days, so it's rotating slower than it revolves around the sun. And it also has an obliquity of about 180 degrees, so it's a retrograde rotator. But we don't know how Venus's spin has evolved in the past. And so we don't know if it was rotating slowly enough in the past to form the strong cloud cover to keep it habitable for these long timescales. And previous studies that have thought about a long-lived habitable Venus have assumed that its spin has been constant in time with the slow spin state that it has today. So why does Venus spin this way? It's a very bizarre rotation state. The the evolution of a planet's rotation is determined by the sum of the torques that are acting on its solid body. So here I'm showing you the rate of change of the angular momentum of the planet. C is the principal moment of inertia of the planet, and big omega is its rotation rate. And in this talk, I'll talk about two different tidal torques. One is the gravitational tide. This one might be a little bit more well-known if you've thought about tidally locked planets. This is a tide that pushes the planet toward a synchronous rotation. In other words, it slows the planet's rotation. And the atmospheric thermal tide pushes the planet away from a synchronous rotation, or it speeds up the rotation rate of the planet. Now we'll do a little crash course in tidal theory. I'll talk to you about the gravitational tide first. So here we have a planet that is rotating with a rotation rate omega. It's also orbiting around its star, and it has a solid body. Because one side of the planet is a little bit closer to the star than the other side, it's experiencing also a slightly stronger force of gravity. And this causes the surface of the planet to deform into what's called a tidal bulge. But as the planet spins, there's energy dissipation in the interior. And so the solid part of the planet cannot instantaneously readjust to the new gravity field. And this means that the tidal bulge is misaligned to the planet-star axis. There's a tidal lag between the orientation. And this means that the gravity of the star can then tug on this tidal bulge. And you can see that the torque that it applies is in the opposite direction to the planet's spin. So if there was nothing else going on, the equilibrium state of this would be tidal locking, where 1 day is equal to 1 year, kind of like the moon is tidally locked to Earth, where the same side faces and the other side always faces away. But on Venus, this is not the only tidal torque acting. There's also an atmospheric thermal tide. So here we have a planet that is also rotating with a rotation rate big omega, and now it has an atmosphere. Because one side of the atmosphere is receiving more sunlight than the other side of the atmosphere, there's going to be temperature gradients between the day side and the night side. And these temperature gradients will drive large-scale mass redistribution in the atmosphere. So this is circulation in the atmosphere, taking it from the hot part to the cold part. And this means that the place that is hot in the atmosphere will have a lower pressure than the cold part of the planet, which will have a higher pressure. So here I'm actually showing you the quadrupole moment of the pressure field, which is just the second order spherical harmonic of the pressure field. That's what's important for torque here. But similarly to the gravitational tide, as the planet spins, the orientation of this pressure bulge cannot adjust instantly to the new location of the sun. And in other words, there's thermal inertia in the atmosphere. And so the hottest part of the planet is not where the sun is, it's where the sun was a little bit ago. So like here in Tucson, the hottest time of day is not noon, it's 3 or 4 p.m. That's because it takes the atmosphere time to warm up. And so now this pressure bulge is misaligned to the planet-star axis. And so the star exerts a torque on the atmospheric bulge. That torque is communicated to the solid body through friction at the surface. And you can see that this torque spins the planet in the same direction as its rotation. So it will speed up the planet's rotation. And the balance between these two opposing tidal torques will determine the equilibrium rotation rate of the planet, where the gravitational tide is slowing the planet down and the thermal tide is speeding the planet up. And it's believed that Venus today is in an equilibrium state between its gravitational tide and its thermal tide. So then the question becomes, if there were past changes in the Venusian atmosphere, would that then lead to past changes in the spin state? And so how does the atmospheric thermal tide depend on the composition or the climate state of the planet? And that was the topic of my first study in this kind of realm. What I did is really quickly before I start this, I'm going to remind you that what's important for the thermal tide is that sunlight is making it to the surface and is driving strong temperature gradients between the day side and the night side of the planet. So that'll help you kind of contextualize these results that I'm going to show you. So what we did in this study is we took a global climate model and we performed targeted GCM sensitivity tests where we varied individually different aspects of the planet's atmosphere, and then we calculated the tidal torque, and this taught us something about how the torque depends on the climate state. So we started with an obvious one. Here I'm showing you the torque due to the thermal tide as a function of atmospheric surface pressure. So as you move to the right on this plot, you're putting more and more mass into the atmosphere. We're holding everything else fixed, so the net opacity of the atmosphere is the same, in all of these simulations, we're just adding more mass to the atmosphere. And so you can see as you have a more massive atmosphere, you have a stronger torque. And this makes sense. There's just more stuff in the atmosphere to tug on. And this is on a log-log plot. You can see that the slope of this line is about 2/3. So it's suggesting that the torque to the thermal tide scales with surface pressure, like PS to the 2/3. This was important insight for us because we're going to develop an analytic model that helps us capture these effects. But what's interesting is that Venus has a very thick atmosphere, almost 100 bars, but its thermal tide is pretty weak. And so based off of this trend, you would expect Venus to have an extremely strong thermal tide due to how much mass is in its atmosphere. But in reality, it's about 2 orders of magnitude weaker than you would expect. So there's clearly more physics happening here that is not just captured by putting more mass in the atmosphere. So next, we held surface pressure fixed at 1 bar. And now all we're doing is changing the long wave opacity in the atmosphere. So we're amping up the greenhouse effect on this planet. We're going to ignore the low opacity stuff because it's not super relevant for this study. But at high opacity, you can see that the strong greenhouse effect from the really high opacity of the atmosphere is essentially blanketing the night side. So the night side cannot cool off at night. And this is minimizing the temperature gradients across the planet. And without those strong temperature gradients, you don't have a strong tide. This is maybe giving us a little bit of clues about why Venus's tide is so weak, even though its atmosphere is very massive. It's just very opaque. Similarly, if you perform the test where you ramp up the shortwave opacity of the atmosphere, what you're doing here is you're having solar radiation being absorbed at higher and higher altitudes in the planet's atmosphere. And this also weakens the tide for 2 reasons. One, if all of the radiation is being absorbed high up in the atmosphere, none of it is making it to the surface, which is where all the mass is, which is where you want to drive this tide. But also you're stabilizing the atmosphere to convection. So now you actually can't form this large-scale mass redistribution because you're inhibiting convection in this planet's atmosphere. And both of these things lead to a weak tide. And so using the results of this GCM test, we developed an analytic model which captures the qualitative behavior of how the tide depends on the atmospheric properties of the atmosphere. And what the study pointed us to was that high opacity atmospheres like Venus have weak thermal tides. And what this analytic model is going to help us do is perform many, many simulations on giga-year timescales, which is not feasible using a global climate model. So just to recap, modern Venus, though it has a very thick atmosphere, it has a very weak tide, and that's because its atmosphere is very opaque. And this, because the thermal tide is so weak, Venus can rotate slowly, because the thermal tide is the thing that's going to try to speed it up. Versus if Venus was habitable in the past, this like Earth-like atmosphere would actually generate a much stronger tide, almost 10 times stronger. And this means that its rotation would actually speed up. But remember what I told you for a habitable Venus is that we need strong cloud cover. And in order to do that, Venus needs to rotate slowly. So now the question becomes, can you have a self-consistent, long-lived habitable state if you consider contributions from climate dynamics and spin dynamics? How are we feeling so far? Any questions?
Okay. Yes, if I may. Can
Sure.
you hear me? Hi. So I just wanted to make sure my understanding is correct of the statement that in order to have a strong cloud cover, you need a slow rotation, and it's kind of a chicken and egg question. Like, so my understanding is that if you have a slow rotation, that the substellar point is going to spend a lot of time at the same location. So this is going to enable the possibility of a strong cloud cover. Is that what you're saying?
Yes, that's exactly right.
Okay, and so once you got your strong cloud cover, it's going to slow the rotation, right?
So once you have a habitable Venus, the atmosphere allows pretty much most of the radiation to make it to the surface, and this drives a very strong thermal tide. And so even if you start with a slow rotation, which allows you to be habitable, once you are habitable, you'll be pushed towards a faster and faster rotation rate. And so there's kind of a limited amount of time that you would be able to stay, and that's
okay, so in other words, the strong cloud cover that we are having today is not thinkable at the start of Venus's life. Is that what you're saying?
Oh yes, great question. So Venus today does have very strong cloud cover. It's like a sulfuric acid haze. And actually it's such a strong cloud cover that Venus's equilibrium temperature is below that of Earth, even though it receives twice as much solar radiation. But the thing is, it's very difficult to form sulfuric acid clouds in a habitable state because all that sulfur just wants to dissolve into the ocean. And so these are water clouds that we're creating here. They're different from the clouds that are on Venus today.
Oh, thank you so much. That's very enlightening. That answers my question. Thank you.
Thank you for the question. Okay, now that we're all on the same page, now we're going to launch into the meat of it. I'm going to show you our spin climate coevolution model for Venus. Okay, so we are going to model Venus's evolution from the beginning of the solar system all the way to today. And we're going to consider how the sun has brightened in time, because that'll be very important for determining if Venus is habitable. Importantly, we don't know what Venus's initial spin state was. And so we're going to perform many, many simulations where we insert random initial conditions for Venus's spin state and allow it to evolve in time. We're going to consider tidal effects from the gravitational tide, which remember is going to slow the planet's rotation in time. We're also going to include core mantle friction, which I know I didn't explain, but the only thing you need to know about core mantle friction is that it also slows the planet's rotation in time. And then we're going to model how the atmosphere evolves in time, and changes in the atmosphere will drive changes in the thermal tide. So at the very beginning of the solar system, if Venus formed with water, the heat of formation would have made the surface too hot for that water to condense, which means that the water would have existed in the atmosphere as steam. Now, water is a very good greenhouse gas, and it absorbs stellar radiation or solar radiation. And so this would be an extremely opaque atmosphere, even more opaque than Venus is today. And so the thermal tide in this case is essentially zero. Which means that while Venus is in the steam atmosphere state, the only thing that's happening is the gravitational tide and core mantle friction. So it'll only be slowing down in that time frame. But also, we don't know how long Venus spent in this state. And so we're going to treat the duration of the steam atmosphere state as an additional free parameter that we randomly vary in the model. At the end of the steam atmosphere state, which we induce the end of it to make sure that Venus is allowed to have a habitable state, if it's rotating slowly enough, it will transition into its habitable state. In this state, it has an Earth-like atmosphere with a very strong thermal tide. Also, within the habitable state, we include a parameterization for how cloud cover depends on rotation rate. So in the black stars, I'm showing you GCM results from Jun Yang's work in 2014. He pioneered this idea. And I developed a very simple parameterization to explain how the planetary albedo or cloud cover depends on the rotation rate. And I'm also including a dependence on the incident solar radiation. You can imagine if you're getting more radiation, you can drive stronger convection. So that's why you also get more cloud cover. So that is put into the model. So that at each time step in the habitable state, we're calculating how much solar radiation is coming into the planet. We're calculating the albedo of the planet. So now we're getting absorbed solar radiation. And we're trying to see if that absorbed solar radiation is beneath the runaway greenhouse limit. So if at any point Venus is rotating too quickly to have strong enough cloud cover to be habitable, the habitable state ends. Additionally, if the habitable state lasts for a really long time, but we hit 0.5 gigayears ago, we're going to induce a resurfacing event, which will transition Venus's atmosphere to its current state. And this is just to make sure that all of the planets end with the right atmosphere at the end. So in this framework, all of the planets end with a modern Venus atmospheric state, but not all of them end up with the right spin state. So we run this model tens of thousands of times with varying initial conditions and durations of the steam atmosphere state. And then at the end, we sort the solutions based off of their final spin state. Some of our planets end up tidally locked. This is a rotation state where the spin state is equal to the orbital rate. But this spin state is not consistent with what we see today on Venus. And so if the solution ended up in this state, we discard it and we say that's not a consistent solution. Some of our planets end up prograde with a 77-day rotation. in the current balance between the gravitational and thermal tides of Venus's current atmosphere, there's actually two equilibria. One is this prograde equilibrium, and the other is the retrograde equilibrium we see today. So there's kind of like a 50-50 chance it would have ended up in that prograde state. But those are also not consistent with what we see today. So we're going to discard those. Luckily, some of the planets do end up with the right spin state. Otherwise, this would be a boring talk. So these are the planets that end with a spin state that is consistent with what we see on Venus today. These are the good ones. We're going to focus especially hard on these. But also, there are a lot of solutions that just don't spin down to either of these or to any of these equilibria over the age of the solar system. These tend to be planets that started with a very rapid initial rotation rate, and there's just not enough time for them to spin down in 4.5 billion years. But these are also not consistent. Here I'm going to show you how the initial spin state and the duration of the steam atmosphere state affect the final spin state that these planets end up in. And I've divided this graph into two different boxes. On the top, we have planets that were initially prograde. And so these are planets whose initial obliquities were under 90 degrees. And then we have initially retrograde solutions where their initial obliquities were above 90 degrees. Okay, I'll show you the tidally locked solutions first. There are kind of two things that are happening here. One is that if the planet starts initially with a very slow rotation rate, which is closer to the center of these graphs, they're much more likely to end up tidally locked. And that's because they're starting already pretty close to the tidally locked equilibrium. So they kind of fall into that equilibrium much easier. Versus it can also end up tidally locked if it spends a really long time in the steam atmosphere state. And this also makes sense because remember, in the steam atmosphere state, the atmosphere is so opaque that there's essentially no thermal tide. So all that's happening there is the planet is slowing down and moving towards the tidally locked equilibria. And so if it spends a long time in that state, it's very likely that it will end up tidally locked. But this is interesting because these states are not consistent with what we see today. So what we're doing is kind of carving out a parameter space that maybe is not explained by Venus's current spin state. Oh, I also should have mentioned that if any of these dots are circled in red, that means that they never experienced a habitable state. And those tend to be planets that started with a very rapid rotation rate. So by the time they were allowed to be habitable, they were spinning too fast to form strong enough clouds to be habitable. So they were never habitable. Here are the planets that don't equilibrate over the age of the solar system. And you can see that they just tend to be the fast initial rotators. But this also could be really interesting when we start thinking about Venus's initial rotation period. And so maybe what this model is doing is excluding some of these scenarios. Here's the prograde Venus solutions. You can see that planets that start prograde in the top box tend to stay prograde, and that's why they end up in the prograde equilibria. But there are a few solutions in the bottom that do manage to flip their spins over time. And this is a known thing that is interesting, but I'm glad that our model could also show this. And then finally, the main event is the Venus solutions. These are the orange dots. Like with the prograde equilibria, these solutions tend to start retrograde because this is a retrograde spin state, but there are a few solutions that manage to flip their obliquities over this integration. But so far, I've told you nothing about habitability, so that's what we're going to get into next. I'm going to show you a sample trajectory from one of these Venus solutions. So here I'm showing you rotation period as a function of time. So moving up on the graph is a faster rotation rate, and this is a weaker cloud cover. In this red region, this is the runaway greenhouse region of spin states. So any rotation rate that falls in this red region is too fast to have strong enough cloud cover to be habitable. And you can see that it becomes stricter and stricter over time in the sense that you need slower and slower rotation rates as the solar system evolves. And that's because the sun is brightening. So you need more and more cloud cover, which means you need a slower and slower rotation rate. On the bottom, I'm going to show you torque, which will help you kind of understand why the rotation is evolving the way it is. And so positive torque here will mean the planet is spinning faster, and negative torque means the planet is spinning slower. So keep your eyes on the bottom plot. The solid black line is the net torque and this is the sum of all of the individual torques acting on the body, which I'm showing in the other colored lines on the torque plot. So for example, if you start in your steam atmosphere state, like I said, this is a very opaque atmosphere, and so the thermal tide is 0, and you can see that in the blue line. The torque due to the atmospheric tide is 0. So the only thing that's acting is the gravitational tide and core mantle friction. Both of those are negative torques, so the net torque is negative, and the planet is going to spin slower. It's going to move towards a slower rotation in this spin state. This is a log axis for time though, so you can see the planet's not really spending that much time there, and that's why you're not seeing very much spin evolution. But at the end of the steam atmosphere state, its rotation is slow enough, it's outside of this red runaway greenhouse region, such that it can be habitable. So then we transition the planet to a habitable atmosphere state, and the strong thermal tide in this state, you can see the red line bumps up because the atmospheric tide becomes very strong. It flips the sign of the net torque. So now the net torque is positive, and the planet starts spinning faster. You can see that in this orange rotation period versus time. It's spinning faster and faster until it intersects with the runaway greenhouse region, which means now it's spinning too fast to form strong enough cloud cover to be habitable. And so the habitable state ends, and then it transitions to modern Venus's atmospheric state, and for the rest of the simulation, it's moving towards Venus's current spin state. And so the mechanism here that's ending the habitable state is that the thermal tide is so strong in the habitable state that it spins the planet faster to the point where the planet can't sustain cloud cover anymore, and it ends its own habitable state. Okay, any questions here?
So I probably missed something fundamental, but why does the torque due to the atmospheric tide, why is that such a sharp change?
Yeah, so in this model, we're transitioning the climate pretty much instantly in time because the climate will adjust so much faster than the spin. So we're doing instantaneous changes in the climate state. And then the reason why this climate state produces such a strong tide is because you have so much solar radiation making it to the surface and driving such strong circulation on this planet that you're making big pressure gradients. And that is what's driving the tide.
So what's really driving this is the increasing solar luminosity, yes?
So the thermal tide does have a dependence on the solar luminosity, but what's really driving this is just that different atmospheric compositions have different thermal tides associated with them. So even though Venus today has a very thick or very massive atmosphere, so little sunlight, like percent levels of sunlight, make it to the surface on Venus, and the strong greenhouse effect keeps the temperature gradients so small across the surface that you just can't drive this strong circulation and make these pressure gradients between the day and the night side.
So then I'm totally missing something. What, if it's not the solar luminosity, how is the composition changing?
Of the planet.
Yeah,
So I guess what we're assuming happened here is that it was in a steam state and it's slowly cooling off. And at some point, the surface is cool enough that you can condense water onto the surface. So that's how you transition to a habitable state. You stay in the habitable state as long as you have enough cloud cover to protect it from the runaway greenhouse. And then once that habitable state ends, we're making the assumption that it just becomes modern Venus's atmosphere, but there's definitely a lot of room there to think about like how the atmosphere was outgassed in time. This is a conservative assumption to make sure that we maximize the number of states that end up looking like modern Venus. And so solar brightening is important in the sense that it requires a slower and slower rotation rate in time. But even if we held the solar constant fixed, which we did in some sensitivity tests, this mechanism still operates because all that's happening is it's really the planet spinning faster that is ending the habitable state.
but you said the composition is changing. That's what's driving it. And the composition is changing because there's a transition from steam to condensed state.
Right.
And that's happening because the planet is cooling off.
So if you're imagining the planet is formed hot because a bunch of stuff just crashed into it. So now it's hot from formation. It's too hot to let water condense, but it's cooling off over time to the point where it can condense the water.
I see. So it's not in equilibrium with the solar
That's right.
installation.
That's right.
Okay, which is quite different than what happens on Earth currently.
But I should say that whether or not Venus actually was able to condense its water is definitely still up in the air. Venus might be so close to the sun that its equilibrium state in the steam atmosphere state is a runaway greenhouse. And so, but I think we're kind of giving the habitable atmosphere its best chance in this model by forcing the steam atmosphere state to end. Good questions. So how long were these habitable periods? There's two things that we care about when it comes to characterizing these habitable states. We care how long they lasted, but we also care how recently they occurred, because if we want to observe evidence on Venus of these past states, it's much easier to do if they were recent. Okay, so I'm going to show you the duration of the habitable state in gigayears as a function of its initial rotation period. And these are only the solutions that ended with a modern Venus spin state. So there's a lot of interesting things going on here. I think the one that should catch your eye maybe first is that the maximum length of the habitable state is 0.7 gigayears, which I gave this talk a little bit ago and called it short-lived. And people were like, okay, well, what is your criteria for something being short-lived versus long-lived? Short-lived here, we just mean that it's much shorter than this 4 billion year long habitable state on Venus that has been proposed previously. The other thing you should notice is that the length of the habitable state increases the slower your initial rotation period is. So let's try to understand this a little bit. We're going to define a spin-out timescale, which is essentially how long does it take the thermal tide to spin it from some initial rotation period to that critical rotation period where it's rotating too fast to be habitable. So here I'm showing you again the net torque equation. In the habitable state, the thermal tide is so strong that essentially it's dominating the torque balance. So we're going to assume that the thermal tide is the only torque here. And then on the right, I'm showing you this analytic form of the thermal tide, which we developed from our GCM study, where sigma here is called the forcing frequency. It's the difference between the spin rate and the orbital rate. These are constants that are describing the strength of the tide. And this term here is the rotation rate dependence of the tide. So what we're going to do is we're going to integrate this equation. And we're going to write an analytic function for the total time spent in the habitable state as a function of its initial spin state, which is the sigma naught, and the critical rotation rate, which is the sigma RG. That's the runaway greenhouse threshold. And here I'm just plotting this analytic form on top of our solutions. And so you can understand this result by thinking, okay, what the thermal tide is doing is it's spinning the planet from a slow rotation rate to this critical rotation rate. And so the slower that initial spin is, the more time the thermal tide needs in order to spin it out. So that's why the habitable states are longer if you start with a slow rotation rate. So it's pretty straightforward. Another interesting thing about these results is that we actually can't get a modern Venus solution unless the initial rotation period was slower than 4 days. And this is kind of a classic thing that comes out of Venus evolution models, where if it starts with a fast rotation rate, it's very difficult to get it to spin down over the age of the solar system. But from planetary formation models, we kind of expect rocky planets to start with fast rotation rates. So here I'm plotting just a few rocky bodies, not necessarily planets, in our solar system. And they all have very rapid rotation rates, like under a day. And so what this is suggesting is that we either need a giant impact to occur on Venus, which took some of its angular momentum early on, or there is maybe some additional dissipation mechanisms that haven't been considered in this model that could be relevant to explaining why Venus rotates so slowly. So I told you we care about the length of the habitable state, but we also care about how recently this habitable state occurred. So here I'll show you duration of the habitable state as a function of the last habitable time in gigayears ago. I'm also showing you our spin-out timescale again. What you can see here is that in our model, these habitable states are only long if they occurred very early in the solar system. So on the right, that would be today, and on the left is the beginning of the solar system. And they decrease in duration as you move to more recent habitable states. And this also makes sense because the sun is brightening in time, which means that critical rotation period that you need to stay habitable gets slower and slower. And this makes the spin out timescale shorter and shorter because it's so much easier for the thermal tide to spin it out. And so this is suggesting that if Venus was habitable in the past, it was short-lived and it was ancient. And so if we go to Venus and we start searching for evidence of water on the surface in the rock record, this can get a little complicated because, like I told you, the surface of Venus is very young because it's been covered with fresh volcanic material. And so I marked this resurfacing event, which is the average age of the surface. But then, luckily, Venus has these regions called the tesserae, which are above this floodplain, which may hold evidence of past water-rock interactions, but they're also not, their age is also not like the full age of Venus. And so here I'm showing you just estimated ages of the tesserae on Venus. And so what our model is suggesting is that if we go to Venus and we study these highland tesserae, we may be unlikely to actually see evidence of these past habitable states in the rock record. So just to summarize, what this work is showing is that if you had a habitable state on Venus, it would be short-lived and it would be ancient. And this is because the atmospheric thermal tide spins the planet faster, and this terminates the habitable state. So going forward in my postdoc, what I want to do is both deepen this analysis to think about other pathways that Venus could have taken, but also zoom out to think about how this mechanism could affect Venus-like exoplanets. So the gravitational tide actually has a much stronger dependence on semi-major axis than the thermal tide. You can see it's 1/8⁶ versus 1/8�3. And what this means is that if you're looking at habitable zone planets around small stars, their semi-major axis is so small that the gravitational tide is going to dominate the thermal tide. So we expect these planets to be tidally locked, and so the spin-out mechanism is not going to be important on these planets. Versus planets that orbit sun-like stars, or even case-type stars, their thermal tide and gravitational tides will be much more comparable, which means that the dependence of the thermal tide on climate state will become important, and these planets could be vulnerable to this spin-out mechanism. So something I'm interested in exploring is mapping out the parameter space in which we expect the spin-out region, or the spin-out mechanism to be important. And then also realizing that it's not that these planets will never be habitable, it's that they're going to be transiently habitable. And so how many of these planets would you actually need to observe to catch one of them in its short habitable state? I think that would be a really interesting question. And then thinking more deeply about Venus, we talked a lot about this long-lived habitable Venus scenario, but this was only one scenario for Venus. It's also possible that Venus, like we talked about a little bit earlier, was just steamy forever. The water never condensed on the surface, and the atmosphere was slowly lost in time from hydrogen escape. And so I want to take this framework and apply it to these other evolutionary pathways. So for example, take a steamy Venus. If it had this really thick water atmosphere, its surface could be so hot that it actually melts the rock at the surface. And this could form a magma ocean. On Earth today, actually most of our tidal dissipation occurs in the ocean, from the fluid response of the ocean to the tidal effects. And so if Venus ever had a magma ocean, it would be important to consider the fluid response of the magma ocean. And this could actually really enhance tidal dissipation and cause a much stronger gravitational tide. And that could help us explain why Venus has such a slow rotation rate. Maybe it could have formed with a rapid rotation rate if this mechanism was occurring. So over time, what would happen is water in the atmosphere would be lost from photolysis and hydrogen escape. And as the atmosphere gets thinner, the surface would get a little cooler, the magma ocean would shallow, and over time, you would lose your atmosphere and you would stop having this magma ocean state. And so what I'm going to do is take this framework and think about a time-evolving steam atmosphere state with a time-evolving magma ocean. And I'm going to ask two questions here. One is, can the magma ocean spin down a rapidly rotating Venus? Which would be really interesting because then you wouldn't have to invoke something like a giant impact, striking Venus with a very specific impact geometry. Another question you can ask is, okay, well, if it spends too long in the steam atmosphere state with a strong magma ocean spinning it down, then most of my solutions are going to end up tidally locked, which is not consistent with what we see today on Venus. So maybe this can help us constrain the water loss rates on Venus. Another option is that Venus just formed dry or lost its water very quickly and that its atmosphere was slowly outgassed or catastrophically outgassed at some point in its history. And this too would lead to a time-varying thermal tide. So here I'm showing you thermal tide as a function of surface pressure, but unlike my GCM study, I'm including the fact that as you increase the surface pressure of, say, a CO2 atmosphere, you're also going to increase the opacity of the atmosphere. So on the left, you just have low mass atmosphere, which leads to a weak tide, versus on the right side, you have a high mass atmosphere, but also high opacity, and that's also leading to a weak thermal tide. And somewhere in the middle, around like 1 to 10 bars, you get a very strong tide. And so what I'll do, and here's Venus today, where it has this high mass, high opacity atmosphere and a weak tide. And so what I'll do is I'll study different outgassing scenarios, which can be tied to tectonic regimes on Venus, by plotting rotation rate as a function of time, corresponding to different surface pressure versus time scenarios. So for example, this will be modern Venus's rotation rate. If you had a scenario where Venus pretty much outgassed its entire atmosphere very early in its history, that would mean that its rotation rate has a long time to get it to its current rotation rate. Versus if the atmosphere was outgassed very slowly in time, it's going to spend a lot of its history in this 1 to 10 bar, very strong thermal tide regime. And maybe in that case, you won't actually have enough time to get the planet to its modern Venus rotation rate. So this would be using Venus's current spin state as an additional constraint on its outgassing history. Okay, I'm giving you a lot of information, so I'm just going to put my key takeaways up here, and I hope you have lots of questions. And thanks for listening.
Really excellent talk. I was wondering about a carbon cycle, like if there was a state that could be allowed with carbon, CO2 going into carbon and rocks, would that change the scenario? And maybe is that reason that didn't happen?
So you mean like in a more habitable state if you had an active
during
carbon
the
silicate
habitable
cycle?
state, yeah.
Yeah, so for example, in our the original model that I presented mostly about, we had to guess something about its greenhouse gas concentration, and so we assumed that it was in balance with its carbon silicate cycle. For the project where I'm going to think about outgassing rates, in that one I probably will assume that it was never habitable because there was just never water on the planet. But I will have to think about sources and sinks of CO2 in that case, just to connect volcanic outgassing rates to actual atmospheric inventories.
I have a question online. Virginia, do you want to speak up?
Hi. Well, thank you so much for that talk. I wish I had given like such lively talks during my PhD. Look, I have a question about, so you've been taking a look at the whole spin evolution. And so what I wanted to know is if you took a look only at the value of the rotational spin, or if you actually took a look at the orientation of the planet and the spin axis itself.
Yes, great question. Yeah, so what I glossed over is that this model considers spin evolution, but also obliquity evolution. So I'm starting, many of my planets start with obliquities that are different from 0 or 180, and then they evolve in time.
Excellent. Yeah, but my question was about, because I was thinking about the work of Jacques Lascar on dynamics and how the obliquity of terrestrial planets was likely very chaotic. So I was just thinking if this was something that you had taken into account that to some extent in there, and if it could potentially explain some of the things you do not manage to explain, but that's probably another PhD.
No, that's a lovely question. And Correa and Lascar's work on tidal evolution on Venus was the motivation for this study. So yes, it is possible that Venus underwent chaotic obliquity in its history, like similar to what Mars is experiencing today. And this has a lot to do with its precession rate being in resonance with Jupiter, whatever Jupiter's doing. In this model, we're kind of considering Venus in an isolated state, so things like Jupiter are not included here, and so we don't have any chaotic obliquity in here. What I would say to argue towards the validity of this model is that if Venus was chaotically evolving in obliquity in its habitable state, I think that would make it pretty difficult to stay habitable, so us kind of keeping the obliquity evolution smooth is probably pretty conservative, but yeah. I mean, great question. So much dynamics. When I was talking to Renu earlier, she asked me if I was doing orbital evolution too, and I said, oh no. But yeah, definitely very interesting.
Thank you.
I already asked questions. I was gonna say, how much would a water ocean on habitable Venus affect this?
Oh, you mean from the tides?
Yeah.
Yeah, wonderful question. So the short answer is we don't know. We barely understand how the tides work in the ocean on Earth today. So for example, if you take the current tidal dissipation in Earth's ocean today, it's very strong. It's actually so strong that you would expect that the moon would only be 1.5 billion years old because of how quickly the moon is recessing today. And there's been a lot of work thinking about, well, maybe Earth's ocean is just in a very specific resonant state because of its rapid rotation and like the width of the Atlantic basin. You know, it's all very complicated. If there was a water ocean on Venus, I think a lot of models have, there's been one paper that has thought about what the tidal dissipation would have looked like in a putative Venusian ocean. The thing is, you need it to be rotating pretty fast in order for there to be these resonances with the ocean. And actually, you can't have it be rotating that fast and have an ocean, because then it wouldn't have the strong cloud cover. So we did not include ocean tidal dynamics in this model. And our justification for that was that in order to get the tidal dynamics to be strong enough, it needs to be rapidly rotating, which you can't do because then there wouldn't be an ocean.
And a question about, could you elaborate a little bit more on how do you model the cloud formation or presence of clouds as a function of spin rate?
Mm-hmm. So what?
Yeah.
So what we did is we assumed that the vigorousness of convection is really just scaling with the temperature gradients across the planet, which I think makes sense. Like what's driving this large scale of circulation is getting stuff from the hot part to the cold part. So in the thermal tide model, there is a function for the temperature difference between the day side and the night side. So what we did is we took that same functional form and tweaked it a little bit to represent albedo instead of temperature gradients. And then we fit, I think, one key parameter in order to, let's see where it is. Oh, sorry. So here, the red line is our parameterization based off of the temperature gradient idea. And then the stars are actual GCM results from Jean Yang's work. And so with one fitted parameter, we reproduce the trends here pretty well. I think another thing I'd like to do in my PhD is actually, now that I've explored this huge parameter space, is run like a targeted trajectory in a GCM where I take the planet, give it a slow rotation, let it form its clouds, calculate the tide, push the rotation rate a little bit, let it equilibrate and keep pushing it to show that in a model that includes actual cloud physics, this results and it still holds.
So in very silly questions, okay, so in most optimistic case, how long could you make the habitable phase last? Is it 700 million years that you were saying?
That is the longest that our model was able to produce. We also did a bunch of sensitivity tests here because obviously there's so many unknowns, like the rheology of Venus's interior, or even just, okay, what if it didn't have an Earth-like atmosphere? It had 2 bars in the atmosphere instead of 1 bar. And in all of those cases, it was under 1 billion years.
And that habitable condition, 700 million years was the maximum. How often actually, and what is the fraction of them? The entire case is what fraction of them had about 700 or so?
Oh, I don't know what fraction. I mean, of all the simulations I ran, only 10% of them even ended with the right spin state. Most of them were not equilibrated. Of those, I think a few percent had very long lived. For the most part, they had very short-lived ones, but it's also hard to assign percentages because I'm like initializing these spin states, but I have no priors on like the probability distribution. So I didn't say any percentages on purpose because they kind of don't mean anything.
So you mentioned the spin flip.
Mhm.
What were the circumstances under it? I mean, you have a one-dimensional model.
Right.
Is it just an oversimplification because of that, or is there some physics behind it?
No, I think there's some physics. I think what's happening is that as the planet is spinning down, its obliquity has not yet reached 0 or 180, and so it can pass straight through the tidally locked equilibria. And so what happens is it spins slower and slower and slower to the point where its spin hits zero and then flips around the other way. And so that only occurred in our model for the solutions whose obliquity had not leveled out yet. And the thermal tide kind of drags it the rest of the way through.
So usually by spin zero, you mean it's spinning at orbital rate.
No, I mean, it actually, like omega became zero. So like the frequency would be zero if it was tidally locked. But in that case, it has a positive prograde spin state and slows down so much that it actually starts spinning the opposite way, not because it's obliquity flipped, but because the spin actually changed direction.
Not sure I'm following that. So you're saying it's not crossing through the orbital rate.
It is. It's passing through the tidally locked equilibria, but it doesn't get captured there because the
Okay, so
obliquity is
it
not
is-
zero.
Okay.
Maybe one more question. So if you mentioned exoplanets, so trying to extrapolate from these two exoplanet population potentially. So if you imagine basically just sampling many of these Venuses during their evolution phase, it looks to me that you could probably identify in the parameter space, say the albedo, presence of water, and rotation phase, certain parts that are allowed in the parameter space and others are not consistent with this evolution. Is that correct?
Sure, like, give me an example.
For example, if you basically, the habitable state, right, is only consistent with certain rotation rates, and then also has a consequence of the albedo. So they would all go together. Are there other, so that would be the most obvious one I see from this evolution. Are there other combinations that are allowed or not allowed, or you would see correlations, trends between parameters that could be tested in our population?
Yeah, I think that one other thing that's important here is that we're kind of giving the habitable state its most optimistic, like we're allowing it to happen. But I think something I would be concerned about when it comes to the spin-out hypothesis on the other planets is that they're probably too close to the star for their water atmospheres to ever condense and into an ocean anyway. And so I think that if we looked at a huge population of Venus-like planets, I think we're probably even less likely to see them habitable than this model would suggest, because I think the water ocean probably would never condense.
So a follow up on that, because I was thinking similar to where Daniel was heading. What happens if you remove this end constraint? Where you end up with current Venus?
Yeah.
Can you actually sample the given starting conditions that seem plausible? Can you sample the ending distributions? Because coming from a perspective of someone looking for exoplanets, your distribution plots were much more interesting to me than the which ones match Venus today, which is
that's why I threw a lot of plots in there to get a little bit.
And so can you, if you, how critical is that end constraint on the model actually functioning?
It's actually not that it's not that important. For Venus it is, but if you're zooming out and thinking about exoplanets in general, when I showed you the kind of populations here and showed you all of these final states, all of them had very short-lived habitable states except the tidally locked ones. And that's because once you're tidally locked, it doesn't matter how strong your thermal tide is, it's such a strong equilibrium that the thermal tide can't push you out of it. And because that's a very slow rotating state, those solutions were habitable for the entire simulation.
Because I'm thinking ahead to planets that we might actually be able to detect in the near future, it would be very interesting to run this on super Earths.
Yeah.
And a range of super Earths, because, for the hotter stars, because that, of course, on Chester's plot is the gap that was there 15 years ago and is still there, that we don't have planets up there. The M-dwarf planets are clearly a problem for other reasons, but yeah, it'd be really interesting to see these for that population.
Yeah, definitely. I think if you were
find them soon.
If you were to look at Venus-like planets around sun-like stars, I think that you would mostly find them not habitable, so you'd see them in a runaway greenhouse state. And if you were seeing them habitable, it's very likely that they're tidally locked. And that's what's
a very useful result.
Yeah.
Kind of similar to that question, do you think you can use this sort of cloud feedback configuration to apply to maybe more Earth-like planets? And a follow-up to that is, do you think this could perhaps change how we think about the habitable zone?
I think it could change how we think about the inner edge. I think there's been a lot of work that shows that the inner edge is very sensitive to rotation rate, and it's because of this cloud feedback. For Earth, Earth is far enough into the habitable zone that it doesn't matter how fast it's rotating, it's safe from the runaway greenhouse. But I think that when we're thinking about planets like Earth, like sure, I think this cloud feedback is important, but it probably won't make or break the habitability of planets that are squarely in the habitable zone. It's more for these edge cases where it could be habitable if they had the right conditions, but it kind of depends on what their albedo is.
Are there any last questions? Okay, we're at the top of the hour, and let's thank our speaker.
And let me briefly mention that Andrea is here today and